8.7.1 Graphs of Rational Functions. Some rational functions create very different kinds of graphs from those we are familiar with. In this lesson, we will learn how to predict some of the features of a rational function's graph by studying its equation. When examining a rational function, it will often be helpful to look at the equation in factored form. Now here are three different graphs that we've never seen before. This first one, I could look and I could be like, I have an idea where asymptotes might be, but I don't really know if something else might be going on. So today we're going to learn how to find a little bit more of these asymptotes. The second one here, well, it's a continuous function, and I don't know how to square the bottom of my parent function and add 1 to it. And the last one, I've never even seen anything like that. So today, we're going over how to get at least key points of such equations. We've seen that rational functions have regions that are undefined. These undefined regions can be written in the form of an asymptote or a hole in the graph. For x minus 2, we've done it before. We know how to find the asymptotes of this graph. But today, we will also be looking at holes, just a single point that's undefined. Vertical asymptotes. The equation of the vertical asymptotes can be found by finding the roots of the denominator. Holes. A hole in the graph occurs at values that make both the denominator and the numerator 0, provided there are no vertical asymptotes at these values. Horizontal asymptote. Now there are three different ways we can identify our horizontal asymptote. The first, if the degree of the numerator is less than the degree in the denominator, the horizontal asymptote is simply y equals 0. The second way, if the degree of the numerator and the denominator are equal, the horizontal asymptote is y equals a divided by b, where a and b are the leading coefficients of the numerator and denominator. 3. If the degree in the numerator is greater than the degree in the denominator, there is no horizontal asymptote. Here's an investigation directly from our book. First of all, I'd like to see if there's a vertical asymptote. So, I need to find the roots of the denominator. So x minus 2 equals 0. I have a root at x equals 2. So I know my vertical asymptote is at x equals 2. As my horizontal asymptote goes, I use rule 1 from the previous list, because the degree of the numerator, which is a constant, is less than the degree of the denominator, which is degree 1. Y equals 0 is my asymptote. Now, look for my vertical asymptote again. I find it to be x equals 2, but I also have to check for any holes. So since my numerator isn't constant, I would plug in 2. I would see 2 minus 2 is 0, divided by 2 minus 2 is 0. So in fact, x minus 2 is a hole, as opposed to a vertical asymptote. Y equals 1 over x minus 2 squared. Well, that's a constant over a second degree polynomial. So I know my horizontal asymptote is at y equals 0. If I were to find the two roots of my denominator, they are both at x equals 2. So my my vertical asymptote here is at x equals 2. Finally, I'd find the root of the denominator, that equals 2. I would check to see if there are any holes, so plug 2 back into the numerator. 2 minus 2 squared is 0 squared, which is still 0, divided by 0. Well, in fact, then there's a hole. Now I could check to see if there is any horizontal asymptote. But since the degree of my numerator, which is degree 2, is greater than the degree of the denominator, which is degree 1, I know for a fact there is no vertical asymptote. Now let us look at one function without the graph. I would like to start checking for either vertical asymptotes or holes in the graph. Well, easiest thing to do, at least the place to start, is to put this in factored form like the first slide said. So this would become minus plus x plus 3 times x minus 1. And the bottom would be factored to x minus x plus x minus 4 and x plus 2. Now looking for either holes or vertical asymptotes. Well, I know that's whenever the roots of the denominator are there. So x minus 4 equals 0. I have one root at x equals 4. X plus 2 equals 0. I have one root at x equals negative 2. Well, they would only be holes if I could plug them into x plus 3 or x minus 1, and either of the two equals 0. 4 plus 3 is 7. That's not 0. 4 minus 1 is 3, and that's not 0. Negative 2 plus 3 is 1. That's not 0. And negative 2 minus 1, that's negative 3, none of which are 0. Therefore, I know I have no holes. And I have my vertical asymptotes are at these roots 4 and negative 2. The next thing here I would like to find is my x-intercepts. And those are the roots of the numerator. So x plus 3 equals 0. One of my x-intercepts is at x equals negative 3. And x minus 1 equals 0. My second x-intercept is when x equals 1. Now I'm looking for y-intercepts. Y-intercepts occur whenever x equals 0, so I will plug in 0 for all my x's. So I would have 0 squared plus 2 times 0 minus 3, which is going to leave me y equals negative 3 in the numerator. Then I have 0 squared minus 2 times 0 minus 8. That just leaves me with negative 8. The denominator. And this equals 3/8. So I now know my y-intercepts are at 3/8 or 0.375. Finally, I'd like to see my horizontal asymptotes. That goes back to looking at the rules. If I look at rule number 3, if the degree of the numerator, rule number 2 in our case, it's when the numerator and the denominator have the same degree, I know y is equal to a divided by b, where a and b are the leading coefficients of respectively a the numerator and b the denominator. Well, 1 is my leading coefficient in the numerator, and 1 is my leading coefficient in the denominator. So I could also write this as 1 divided by 1. Therefore, y is equal to 1. And that is my horizontal asymptote.